Hi guys, welcome back to the channel. Today we'll be continuing our discussion about threads. In the previous video, we had discussed about the notion of lock and unlock around the critical section. We discussed this diagram where we saw if a thread is executing and accessing the shared variables, the other thread should not be allowed access to the same variable at the same time. We saw the value of this program was undefined without lock and unlock around the critical section of the code that accesses the shared variable. Today we'll be discussing how idea of lock and unlock has been implemented using Mutex. We'll also implement the same program once without the Mutex and see that the results are undefined. We are then going to add mutex lock and unlock around the critical section of the code and then see the results are accurate. Let's get started on this one. Mutex actually stands for mutual exclusion. It means if a thread has access to shared resources, then any other thread shouldn't be allowed access to the same resource. To understand this idea, let's look at this diagram. Both of these threads wants to access the shared resource. But with mutex, we would enforce a mutual exclusion so that if one thread is accessing shared resource, other thread would not be allowed the access to shared resources. In this diagram, let's assume thread A starts execution first. It locks the mutex in preparation of accessing the shared resources. Once it has acquired or locked the mutex, let's assume there is a context switch to thread B. Now thread A is in the waiting state and thread B is now in the running state. Thread B also wants to access the shared resources, so it will also try to lock the mutex. Since the mutex was already locked by thread A before, before it moved out of the CPU, thread B will not be able to lock the mutex and would block. Since it will not be able to proceed, let's assume the context switch happens again. Thread A is going to continue its execution. It will access the shared resources and at the end unlock the mutex so that other threads can now access the shared resource. Let's assume a context switch again happens here. Thread A goes back to waiting state and thread B is now assigned the CPU. Thread B would now be able to acquire the mutex. It would unlock, access the shared resource, and then unlock the mutex towards the end so that either thread A or any other thread within the process can access the shared resource. With locking and unlocking of mutex around shared resources, we have made sure that there is a mutual exclusion of threads when they are trying to access shared resources. No two threads would be able to access the shared resources if each thread has a lock and unlock call around the critical section where it tries to access the shared resources. Mutexes can be of two types. They can be either dynamically allocated or statically allocated. This is how we allocate a static mutex. A statically allocated mutex has default attributes. If we want non-default behavior, we do a dynamic allocation of mutex. By dynamic allocation, we can leverage the error checking mechanism available with a dynamically allocated mutex. All the mutex functions are defined inside pthread.h. Even the pthread mutex initializer is available inside pthread.h. To lock a mutex, we use pthread mutex lock function. To unlock it, we use pthread mutex unlock function. Both receive the mutex as their argument. They return 0 on success and a positive error number in case of error scenario. If a mutex is already logged, then pthread mutex lock would block. It would wait until the mutex is unlocked, and then pthread mutex lock will acquire the mutex and proceed further. If multiple threads are blocked on pthread mutex lock, then it is indeterminate who is going to acquire the lock first. One of the thread would take the lock and other threads would continue to block on pthread mutex lock. If a thread has already locked a mutex and it tries to lock the same mutex, it will result in a deadlock scenario. It will always block on this lock call and will never be able to unlock, which might lie in further section of the code. There is a special kind of mutex that supports this error checking and would return a error value when such deadlock scenario is arising. Such mutex can be dynamically allocated. If T2 has logged a mutex M1, T1 cannot call unlock on this mutex. A thread can unlock the mutex only if it owns the mutex. A mutex M1 acquired by T2 cannot be unlocked by a T1 thread. Now let's see an example program where we are going to implement this thread function in two variations. In first variation, we are not going to have lock in and lock around the critical section. And in the second variation, we'll put lock and unlock around the critical section and see how the output varies. I'm going to copy the previous thread program that we had written and we'll be modifying the same program. Let's rename this function as thread function. Let's also add a global variable with initial value of 0 that we are going to access inside our thread function in both the threads. Thread function is going to run a for loop and increment the global variable. The right bound of the loop is passed as an argument to the thread function. I'm going to dereference this argument and save it inside a limit integer variable. This for loop is going to take a local copy of the global variable into a integer variable LOC. It will increment the LOC and write it back to the global variable. Let's also not forget to return a null because that's how thread functions should be. The number of time loop has to be run will be passed as a command line argument. It will be saved in argv0 vector at the first index. The 0th index is always the base name, that is the running program itself. Let's now create two threads, T1 and T2, both with default attributes. Let's also invoke pthread join for both of the threads. Otherwise, there are chances that one of the thread would complete first and the program would exit. The unfinished thread would not be able to complete its work in such scenario. Let's also print the global variable at the end to analyze how many increments did each thread make to the global variable. Last argument in pthread create is the argument we want to pass to the thread function. Let's pass the right bound of the loop to the thread function in both the threads. Output of this program seems to be correct for smaller values like 100, 1000, 10,000. Both the threads are incrementing the global variable properly. This is because for smaller values, one thread would be able to complete and then the other thread is going to run. The point that I'm trying to make is that for smaller values, there will be no context switch between the threads. One thread is going to complete and then the other thread will be able to run. In such scenario, both the threads will be accessing shared variable at different point of time. Only in case of large values, there will be context switch between the threads and they are going to access the shared variable at the same time. The output of this program will be non-deterministic until we enforce a mutual exclusion for the shared variable. We are going to define a static mutex variable and enclose the critical section of the code where we access the shared variable with mutex lock call and mutex unlock call. The mutex variable is also a shared variable between both the threads. Let's run the program now. I expect to see correct output for larger values as well now. But there seems to be some problem. For limit value of 100,000, the global variable should be 2 million. But in some instances, we can see it is less than 2 million. Let's look at the program once again. After taking a closer look, I have observed that there are instances when T2 could not complete its work. This is because we forgot to do a pthread join for thread T2. Let's rerun the program and see the output. The output now seems to be consistent, and for a value of 100,000, the global variable has been updated to 2 million. Let's look at few scenarios where deadlock can happen. We already discussed if we try to lock the same mutex in the same thread, then it is going to block forever. There could be another scenario where thread A has locked mutex 1 and thread B has locked mutex 2. Thread A in the next step tries to lock mutex 2, due to which it will block, and thread B in the next step tries to lock mutex 1, due to which this will also block as mutex 1 is already held by thread A. When threads are locking the same mutex, they should always lock them in the same order. This situation can easily be avoided if we have a hierarchy where we define that mutex 1 has to be locked and then only mutex 2 can be locked. With this, thread B will try to lock mutex 1 first and it will block as the mutex 1 is already locked by thread A. Thread B in such scenario will not go ahead and lock mutex 2, due to which thread A can proceed further and lock mutex 2 as well. It can complete its work and unlock both the mutexes, after which thread B can take mutex 1 first and mutex 2 and continue its execution. An alternate strategy could be try and then back off. In this strategy, thread tries to lock the mutex with pthread mutex try lock instead of pthread mutex lock. If the mutex it is trying to lock is already acquired by some other thread, then try lock will return immediately with an error saying that the mutex is already locked. In such scenario, thread can unlock all the acquired mutexes and retry again after some time. Let's look at the same scenario, and instead of doing a lock, let's do a try lock. Thread A is going to start its execution. It will do a try lock on mutex 1 and proceed. Thread B then can do a try lock on mutex 2 and proceed as well. Thread A will now come to this statement where it tries to lock the mutex 2. Mutex try lock will fail in this scenario because mutex 2 is already acquired by thread B. Thread A is now going to release all the mutexes. Since it has acquired mutex 1, it is going to release mutex 1 and then try acquiring the mutex after a delay of maybe say 5 seconds. Meanwhile, thread B is going to run. It will do a try lock on mutex 1 and it will be able to acquire the mutex because thread A had released mutex 1. Thread B is going to proceed and then do a unlock of mutex 2 and mutex 1 at the end, after which thread 1 can proceed its execution without a deadlock scenario.